So I will talk a bit about our activity in the company on creating integrated circuits, electronics for space. I'm quite lucky because Wojtek that talked before me explained some concepts that I also have included, but then I can do that in much lighter. I also see that there are quite some overlap here between the 4D space and us, and I invite them to come and visit us to see if we can do something together. So, yeah. So the title of this talk is maybe a bit misconception because we are not sensing space. You know, space is what is around us. We are creating electronics for sensors which are used in space. And in particular, we are concerned with sensors for radiation. So I lost this thread there now. So in space, we are our customers are actually concerned with detecting radiation coming from extraterrestrial origins, like the sun, from other galaxies, intergalactic radiation, but also sensing radiation coming from the Earth. And in the end, we try to find applications for these technologies here down on the ground. Obviously, the market for space activity is quite limited, so in order to survive, we also have to find applications outside the space field. The company has been around now for more than 20 years, and we have delivered electronics for sensing in space to many projects, and I list a few of them here. These are names that probably doesn't say you anything. So SWIFT, that's actually this one. AMS is on the space station. CALET is on the space station. STIRO is two satellites orbiting the sun. Super Agile is a satellite orbiting the Earth. Chandrayaan, actually it's the Chandrayaan-1, is an Italian space probe that orbited the moon. It's now crash-landed into the moon some time ago, and they had some electronics from us. Dampe is a Chinese observatory that will be launched next year. Dark Matter Particle Explorer. Astro H is a Japanese mission to look for very high energy gamma rays from outside our galaxy. So the SWIFT spacecraft, which has now been in orbit for 11 years, uses our electronics to read out gamma ray detectors, which are located actually like a half circle in this area. There's two other instruments on this spacecraft. It's listed on NASA's list of the most successful science missions of NASA. I think now, in 2010, they passed 500 gamma ray bursts, and they're still counting. So, as we are mainly concerned with radiation, we have to remember that we do not see very much radiation with our senses and our bodies. You know, the most common, for us, radiation is light and heat. You know, we can feel the heat, we can see the light. That's only a very, very small part of the radiation that is around us on the surface, and even more in space. So, when we talk about radiation, we have to remember light is a small part. This is actually the solar spectrum as it's measured on Earth. This is heat, this is light, what we see. But this spectrum continues, and it's in fact, billion times larger. So, looking here, light is in the middle here. The dimension of a light wave is the dimension of a cell. At larger wavelengths, we have radio, we have microwave, we have what is called infrared, which is the heat. We feel it here. We have the microwave radiation, the size of an insect, radio waves, FM radio waves, 3 meters, and we have long wave radio waves, which are the size of buildings and even larger. On the other side, we go into very small wavelengths, visible ultraviolet, that's what burns you during the summer, X-ray, what the dentist used to see your teeth, gamma rays used in the hospitals to diagnose and treat cancer. This is electromagnetic radiation, but there's also other radiation, which is actually parts of atoms. It can be alpha particle, which is actually a helium atom, beta an electron, and it can be neutrons. On Earth, they don't cause much problems. They don't travel very far. They are stopped by air, paper, and so on. In space, however, we find these particle radiation at much higher energy. So, close to Earth, the most common source is the sun. Wojtek already explained in great detail what's going on there. We have ejecta. Ionized atoms are thrown out from the sun at the speed of several kilometers per second. It takes a couple of days to reach the Earth. Luckily, we are shielded by the magnetic field, and we have this nice displays of aurora. This was actually taken here in Oslo a couple of weeks ago from our office window at night. Then, what does Jupiter has to do with this? Jupiter is much bigger than the Earth, has a much higher magnetic field, traps much more radiation from the sun, and we are going to visit Jupiter in a couple of years with this spacecraft called JUICE, launched 2022, arrival in 2030. In fact, the radiation trapped by Jupiter is so high that any normal electronics will not survive. We will also not survive there very long. So we have to do something special, and that is to create electronics which can stand radiation. Why do we go to Jupiter? Because we are curious what's out there, but again, we are also looking for life. These icy moons on Jupiter probably has more water than Earth. Most of that water is ice, but we have good reasons to believe that below those thick ice sheets there is liquid water. So this spacecraft will study that. Our device will only study the radiation and not look for life. So we are contributing here with an instrument on this. Yeah, so why Jupiter? I just said it. It's like a miniature solar system. Ganymede is the main target, but it will also visit this other. So we see here the relative size compared to the Earth. You see, these are actually bigger than our moon. A bit smaller than the Earth, but still. So lots of ice, liquid ocean layers. We don't know. We'll figure out in 15 years from now on. So we have the same scenario here at Jupiter like we have on Earth. The plasma from sun is trapped by Jupiter's very strong magnetic field. There is an interesting artifact that we do not have on Earth because the moon is too far away, but the moons of Jupiter, they actually concentrate this trapping. So on the, Jupiter has aurora like we have on Earth, but we have nice footprint of the moons. So they make circles in the aurora on Jupiter. Earth, on the scale of this picture, is about this size. So you see the aurora in Jupiter is bigger than the whole Earth. So what are we making? We are making this device here. This one is greatly magnified. In reality, it's only like 1 by 1 centimeter, contains a few 100,000 transistors. They are all designed to stand immense amount of radiation. This goes into a little box, about this size, bolted onto the spacecraft. And of course, we are not doing this alone. The prime contractor is EFASEC in Portugal. This is a physics institute in Portugal, also active at CERN. This is another institute in Switzerland. They have an accelerator. They do a lot of physics studies here, and we are actually making this device there. Okay, so that's the solar system. There is also, most of space is much further out. So we are also observing radiation from very far out. Cosmic rays, extremely high energies. That was wrong. It was started in about 100 years ago with a discovery, of course, in Paris. So they also tried with balloons. This is 1912, 1914. So actually, 100 years ago, they went up to 9,000 meters. That's not too bad. Then we all know that other unmanned balloons, they go high up. But these cosmic rays, they are very high energy. They come in from outside our galaxy, and they create a lot of reactions inside the atmosphere. And they actually go far down below Earth also. Like this one is 500 meters below the surface of the Earth. This doesn't have any practical application here on Earth. But we do this because it's fun and because we are curious. So we study with this, we can study neutron stars, black holes, supernova, gamma ray bursts. So we provide electronics for actually a good fraction of those laboratories. So this is SWIFT, alpha magnetic spectrometer, the calorimetric telescope, Pamela, an Italian, super agile, Astro H. So this is an artist's depiction of these extremely violent processes that leads to this multi-TeV, tera-electron volt processes. Luckily, it doesn't happen very close to us, because if it would happen to one of our neighbor stars, it would probably wipe out life on the face facing that star. So these are large instruments made by huge international collaborations. This is the AMS. It's actually the largest scientific instrument on the ISS at 7,000 kilos. As a particle detector, it is even though microscopic, because the CERN detectors are 1,000 times more heavy, or 10,000 times more heavy. But still, in space, it's quite large. This has been done now for 3 years. Down here is the Callet. It was attached there 2 weeks ago, launched by an H-1 rocket from Japan. So these are connected to detectors. There's a typing mistake there. These are also so. In total, it's like a couple of 100,000 amplifier channels. Yeah, so this is how it looks. The detector, there's 6 square meters of this inside. We deliver this part here. This was assembled in Perugia in Italy. And the high energy particle goes through the detector like this. And there's a magnet, and you can then extract, what is this particle, what is the energy, what is the speed, where does it come from, etc. We also do some work in infrared and thermal radiation. Unfortunately for us, we cannot see infrared radiation. If we could, our night sky would look very different. This is the well-known Orion what is called an image. In infrared, is actually very, very bright. There's a lot of ionized gas there, and we do make a circuit here, about this size, that is used to read out infrared detectors. Again, this one also has an interesting environmental impact. This one has to work at minus 200 degrees C. It's very cold. And here we have good help from the Norwegian Space Center, which has financed quite a lot of this work. We don't, but our customers, they do then, they observe the Earth in infrared. This is from the north of Norway. That's where we are. That's where we are now. And of course, for climatic studies, the energy balance of the planet is very important to understand. And we are contributing with a tiny part into these things. Now we are back down on Earth. We also measure radiation on Earth. Essentially, we try to help in cleaning up accidents and also in the running of nuclear power plants. So this is actually an image from Fukushima. It's an instrument that can image where radiation is in the environment. This is a spent storage pool in a nuclear reactor. So this is a product that we are marketing. So as we know, it's quite a few nuclear reactors in operation. 150 will be decommissioned in Norway. And we are providing a tool here for assaying radioactivity at a distance instead of having to walk around with a counter. We also work a bit on imaging ourselves. And this is a device that contains our electronics. It's used for what we call molecular breast imaging. It's a cancer diagnostics that uses radioactivity injected into the patient. It's a sugar, it's a radioactive sugar that goes to the high metabolic tumor. And after half an hour, 1 hour, you can actually image and you can locate the tumor very precise. So this is actually from a real patient. This is a standard mammogram. The problem here, there's another problem here that was not detected. Actually, the first prototype of this instrument was installed at the Norwegian Radium Hospital about 10 years ago. Unfortunately, the Norwegian activity on the whole instrument ceased and it was moved to the US. So, wrapping it all up. So, imaging radiation from space tells us our position in the universe, our place. Where are we? From Earth, in space, tells us the state of our planet. On Earth's surface, helps us in controlling, the environment. And again, imaging radiation in our bodies helps us in diagnosing disease. Okay, that was all. Thank you.